Evaluating the efficacy of a novel phytase source. Phytase is an enzyme that is commonly used in today's swine diets to help reduce the inclusion rate of inorganic phosphorus sources and to reduce the amount of phosphorus excreted by the pig. How phytase works is that it catalyzes the stepwise removal of phosphates from phytic acid or phytate, which is the form that phosphorus is commonly bound up in cereal grains. Technologically, however, manufacturers continue to improve the efficacy of the enzyme through newer generations of the product. So as these new generations of phytase do become available to the marketplace, it's important that new phosphorus release curves are conducted in order to determine the value that each source of phytase has. Typically, phosphorus release curves are derived from measuring the response variables of average daily gain, feed efficiency, and bone ash values. Thus, this led us to the objectives for the trial. First, to evaluate the effects of a novel phytase source, Microtech 5000, on nursery pig performance and bone ash values. And second, to develop an available phosphorus release curve for this product. For feed manufacturing, all ingredients containing phosphorus were analyzed prior to the initiation of the study in order to determine nutrient loadings. The phytase source was blended with ground corn, and the premix was analyzed at a concentration of 580 FTUs per grams in order to establish the proper inclusion level into the experimental diets. All diets were derived from a single basal batch, and after manufacturing this basal batch, then the subsamples were weighed up into the major ingredient scale. From there, treatment-specific ingredients were then hand-added back into the mixture in order to achieve the final dietary treatments. Here is the composition of the basal batch as an ad-fed basis. It's a standard corn and soybean meal-based diet with an SID of 1.25% and meeting all other SID amino acid requirements. You'll notice that the available phosphorus is at 0.12%. This is the level of the negative control. From there, either limestone or monocalcium phosphorus were added to achieve the final dietary treatment calcium and phosphorus levels. Here we have the experimental diet compositions. In the first three columns, we have the inorganic phosphorus control treatments. These were formulated to be either 0.12, 0.18, or 0.24% available phosphorus. Again, you can see either limestone or monocalcium phosphorus was added to the diets to achieve these levels of available phosphorus. Sand was also included in the diets as a non-nutritive ingredient such that the basal diet could remain the same across all dietary treatments. The next four columns represent the phytase treatments that were formulated at 250, 500, 750, or 1,000 FTUs per kilogram. However, as we drop down to the second table of the analyzed composition of the diets, you'll notice in the bold that the phytase analyzed concentrations were 155, 335, 465, or 780 FTUs per kilogram. It's important to note that we did use these analyzed phytase concentrations in the statistical models throughout this trial. In this study, a total of 350 nursery pigs, initially weighing 15.1 kilograms, were used in a 21-day growth trial. Pigs arrived to the facility after weaning and were randomly allotted to pens within two identical barns. Then these pens of pigs were blocked by barn and then were randomly allotted to one of the 7 dietary treatments. There were 5 pigs per pen and 10 pens per dietary treatment. Our treatments were set up to perform a slope ratio assay with inorganic phosphorus as the control phosphorus source, this being 21% monocalcium phosphorus. The control slope consisted of a negative control formulated at 0.12% available phosphorus, the negative control plus 0.06% from inorganic phosphorus to achieve a final of 0.18% available phosphorus, or the negative control plus 0.12% available phosphorus from inorganic phosphorus leading to a 0.24% available phosphorus. The experimental diets included the negative control at 0.12% available phosphorus, and then either adding those analyzed concentrations of 155, 335, 465, or 780 FTUs per kilogram of phytase. All pigs were fed the negative control diet, again at 0.12% available phosphorus, for 4 days prior to initiation of the experimental treatments. On day 21 of the trial, 1 pig per pen, being the mean body weight, was euthanized with an intravenous overdose of sodium pentobarbital. Fibulas from euthanized pigs were then collected and used for percentage bone ash determination. All cartilage caps were removed from these fibulas, and then the bones were boiled for 60 minutes to remove any other adhering tissue. Bones were dried for 7 days prior to ashing in a muffle furnace at 600 degrees Celsius for 24 hours. Total ash weight and percentage ash were then determined after this. As we transition into results, first I'd like to set up the slides. Along the horizontal axis, we have it broken down into the control treatment with available phosphorus from inorganic phosphorus, and in the yellow bars is the Microtech 5000 phytase diets. Along the vertical axis will be the response variable, in this case average daily gain in kilograms. The data shows that as the amount of available phosphorus increases from 0.12 to 0.24%, we see a linear increase in average daily gain across treatments. Similarly, in the Microtech 5000 diets, we see a linear increase as the amount of phytase increases from 155 to 780 FTUs per kilogram. Similarly, for the final body weight of these nursery pigs, as the amount of available phosphorus in the control treatments increases from 0.12 to 0.24%, the pigs show a linear increase in final body weight. Amongst the phytase diets in the yellow bars, again, there is a linear increase in final body weight from 27.3 kilograms up to 28.3 kilograms. As we would expect for average daily feed intake, there are no statistical differences amongst any of the dietary treatments, whether the amount of inorganic phosphorus or the amount of phytase was increased in the diets, with average daily feed intake ranging from 1.09 to 1.20 kilograms. Finally, for feed efficiency, we saw both a linear and a quadratic response, where when increasing the amount of available phosphorus from inorganic phosphorus from 0.12 to 0.18%, we saw the greatest improvement in feed efficiency. However, when we increased the amount of available phosphorus from 0.18 to 0.24%, we saw reduced improvement in feed efficiency. In the Microtech 5000 diets, again, we saw both a linear and a quadratic response, where increasing the amount of phytase from 155 FTUs to 335 FTUs showed the greatest improvement in feed efficiency, where there is no further response after increasing up to that 780 FTUs per kilogram. As we look at the bone values, first we have fibula ash weight in grams. Similar to the growth data that we saw, as the amount of available phosphorus increases from 0.12 to 0.24%, the fibula ash weight increases linearly. Again, for the phytase diets, increasing the amount of phytase in the diets from 155 to 780 FTUs per kilogram also shows an increase in fibula ash weight up to the highest level of phytase included in the diets. This would be reflective of what we would expect as we make more phosphorus available to the pigs, more should be retained in the bones, thus increasing the weight of the bone itself. Finally, for bone ash percent, as the amount of available phosphorus from inorganic phosphorus increases from 0.12 to 0.24%, there's a linear increase in percentage bone ash. Amongst the phytase diets, again, there is a linear increase from 32.8% up to 36.04% at that highest inclusion level of phytase in the diets. However, it's important to note that even at the highest phytase inclusion level of 780 FTUs per kilogram, they still performed below that of the intermediate control pigs that had a bone ash value of 36.2%. Next, the objective was to determine the available phosphorus release curve. First, the available phosphorus intake per pig was calculated for each pen based on the average daily feed intake and the amount of available phosphorus within the diet. Then, simple regression was used to determine the intercept and slope of each response criteria based on the control inorganic phosphorus treatments. Once these coefficients for each response variable was calculated, then they are inputted into the phytase treatments, and the available phosphorus release was calculated for each concentration of the phytase. Because feed efficiency was not within the linear range for the inorganic phosphorus treatments, a release curve was not calculated based on this response variable. For the response criteria, each change in response criteria, whether it was average daily gain, ash weight, or percentage bone ash, was regressed by the analyzed phytase concentration. The percentage bone ash response was explained the most by the change in the phytase concentration with an R-squared of 0.96 as compared to an R-squared of 0.84 or an average daily gain with an R-squared of 0.80. It's important to note that these values were derived from using treatment means instead of individual pen means. Finally, we have an available phosphorus calculated from the percentage bone ash, again, which had the highest correlation for the response variables. Along the horizontal axis is the analyzed concentration of the phytase in the diet, and along the vertical axis is the available phosphorus released based on percentage bone ash. You can see at the lowest inclusion level of 155 FTUs per kilogram, there is a release close to 0.02%. At the 335 FTU per kilogram level, we see a response just below that of 0.06% available phosphorus release, with no further improvement up to 780 FTUs per kilogram. Overall, this study has provided an available phosphorus release curve for Microtech 5000 phytase when included in nursery diets between 155 and 780 FTUs per kilogram. Release values for this product at these analyzed concentrations range from 0.02 to 0.06% available phosphorus. A special thank you goes out to VTR Biotech for partial funding of this product and the Kansas State University Applied Swine Nutrition team. Thank you.